I forgot to record the first part, but I recorded the morning, so you could just look at the morning. So molarity is temperature dependent, and so as the temperature increases, the volume expands. As the volume expands, the molarity goes down. As the temperature decreases, the volume contracts, the molarity goes up. And so the molarity fluctuates with temperature. Do you want to calibrate the molarity for whatever temperature? No, this is too much of a hassle. And so instead of using molarity, we should use something that's temperature independent. What's temperature independent is the percent by mass. Percent by mass doesn't matter what the temperature is. The grams of solute and the grams of solution aren't going to change. How about the percent by volume? Is that temperature dependent? Percent by volume could be temperature dependent, depending on what's happening with the solute versus the solution in expansion and contraction. The M over V percentage is definitely temperature dependent, but molality is not. Molality is a lot less convenient to use, so we don't use this much. Molality is defined as little m, which is the moles of solute over kilograms of solvent. And so it's usually when we do this, we get the fraction in terms of the total. So it's component A over the total. But in this case, it's the solvent, which is not the total mass. It would just be the mass of water in most cases. But one advantage of molality is it doesn't change with temperature. And so let's take a look at this example here. This is a good one. Example 14-1. An ethanol water solution is prepared by dissolving 10.0 milliliters, 10.00 milliliters of ethanol. This is the density of pure ethanol here. So if we have the volume of pure ethanol, we can get the grams of pure ethanol using the density. In a sufficient volume of water to produce 100.0 milliliters of solution. So this is the total volume. Okay, normally we assume, okay, the total volume in milliliters is going to be the same as the grams. But in this case, we don't have to do that because they tell us the density of the solution. So if we know the density of the solution, rather than assuming that it's 1 gram per milliliter, we can use that to figure out how many grams this is. It's going to be less than 100 grams. It's going to be 98.2 grams. What is the concentration of ethanol in this solution expressed in A, volume percent, B, mass percent, C, mass to volume percent, D, mole fraction, E, mole percent, F, molarity, G, molality. So this is all the units, almost. So the volume percent's pretty straightforward. It's the volume of solute ethanol over the total volume times 100. And so we get the volume fraction, 10 over 100 times 100%. That gives us 10.00% ethanol by volume. Okay, then we go on to the mass percent. So we need the grams of ethanol. So we have the density of pure ethanol here. We can convert the milliliters to grams, 7.89 grams. And then we have the volume of the solution and the density of the solution, so we can get the grams of solution, 98.2 grams. Get the mass fraction, multiply by 100%, we get the percent by mass, 8.03. The percent by volume is 10, the percent by mass is 8. Then we can get the mass volume percent. The mass volume will take the mass of solute divided by the volume of the solution, and we get 7.89. So we get 3 different concentrations depending on which one looking at here, but they're all the same, just different units. The mass volume percent. Then we can get the mole fraction. The mole fraction is the moles of solute over the total moles. So moles of solute would be the moles of ethanol. So we go grams to mole conversion, we got the moles of ethanol. And then we need the moles of solution. The moles of solution consist of moles of solute plus moles of solvent. The solute plus the solvent gives us the solution. So the moles of solute is just how many milliliters of ethanol we use, converted to grams. Once we get the grams, we convert it to moles. So we have that calculation here. Then we need how many milliliters of water or grams of water we have. So we know the total grams of solution. We subtract the grams of solute, we get the grams of solvent. This is 90.3 grams of solvent, which is 5.01 moles. And so 0.171 moles of ethanol over 5.18 total moles gives us a mole fraction of 0.0330 over 1. So the mole percent is just take the mole fraction times 100%, gives us 3.30%. And then we could get the molarity, which is the moles of ethanol over liters of solution. So 100 milliliters is 0.1 liters, 1.71 molar. And then we could get the molality. The molality is going to be moles of ethanol over kilograms of solvent. Kilograms of solvent, that's water. So there's 90.3 grams of water, which is this many kilograms. We get this 1.89 molal. So that's all the composition units there. Okay, then we're going to look at the energetics of solution formation. And so take a look at that here. Thermodynamics of solution formation. You know what we call solution formation? We call this dissolution. The thermodynamics of dissolution or dissolving. We typically break this up into 3 steps, but you know, this is all kind of artificial. It all happens kind of at once anyway. Okay, starting off with the components that make up the solution, the first step here is separating out the solvent molecules. So step 1, we need to break apart the solvent. So break solvent, solvent attractions. In the case of water, we need to break the hydrogen bonding and London forces holding the water molecules together. The water molecules are sticky, and so we got to separate them to make room for the solute. Step 2, we need to separate the solute, and so we need to break solute attractions. Now, I'm going to call it attractions. It depends. It could be IMFs, like London dipole or H bonding, or it could actually be bonds. You know, it depends. If it's a solid solute held together by ionic bonds, we have to break apart those ionic bonds to get it to dissolve. And so both, whenever we break something that's endothermic, and so in step 1, it's going to be endothermic here. In step 2, it's going to be endothermic here. And so breaking bonds requires energy. And so we're going up. This is an enthalpy diagram. Enthalpy is just energy, constant pressure here. And then step 3 is we're going to form solute, solvent attractions. When we form bonds or IMFs, then that's exothermic. And so that should be negative. And so a typical dissolution process is this is going to cost us. This is going to cost us, but look at, if we go on this red trajectory here, then overall, it's exothermic. And so when we look at delta H of solution is just the sum of these steps here. So delta H of solution is equal to delta H1 plus delta H2 plus delta H3. And so overall, if this is exothermic, that's favorable. So solution formation is favorable when delta H is of solution is less than 0. It's exothermic. And so it becomes more stable. It's also favorable when it just breaks even. Let's say there's delta H of solution is 0. There's no change in energy. Or delta H of solution is just slightly endothermic. If it's 0 and slightly endothermic, what's the driving force? Because normally the driving force in nature is we want to minimize energy. So if delta H is 0, then why do it? Or if delta H is positive, look at this is blue arrow, is positive. So we got to spend. You're going to spend 500, another 500. You spent $1,000, let's say gambling, and you only got back 600. Is that very profitable? And so why do it? Maybe it's fun. And if it's not too painful, maybe you'll do it. So maybe it's 500 and 500 and you get back 990. So it's $10. $10, maybe it's worth it. You know. But why would nature do it? Is nature going to have fun? Or does nature really care about that? No. These two, why? And the reason is because of this. There are two driving forces, essentially, or one can think of two driving forces in nature. The first one is to minimize energy. So we can always think in terms of nature. What's nature going to do? If I have this pen here and I let go, what happens? It minimizes gravitational potential energy, right? It's going to just fall down. This is higher gravitational potential energy. That's lower gravitational potential energy. So we minimize energy. But why would the pen go up? Or what if I let it go? If I let it go and it just stayed where it is? Or if I let it go and it went up? Would this fall to the ceiling if I let it go? No. And so why is nature doing that? And the reason is there's one more driving force, which we really haven't talked about, and that is to maximize entropy. The maximizing entropy is the reason why we can have the energy go up a little bit as long as the entropy goes up a lot. And so what happens is when you make a solution, it becomes more disordered. And so entropy, what entropy is, it's given by the symbol S, and it's a measure of disorder. And so this is like, you know, when I was trying to, you know, these old bikes, they had these shoes, brake shoes and stuff, you know, in a drum. Have you heard of like drum brakes? Yeah. And they have springs and levers and all this stuff. So I had no problem. When I was young, I had no problem taking it apart. And then I'd have all these parts scattered everywhere. But I had a hard time putting it back. In fact, I couldn't put it back together. I was unsuccessful. So I got it apart, no problem. But putting it back together, I couldn't. It didn't work after I got some new brake shoes. And so then I was thinking entropy, that's it. You know, because having all those parts scattered, that's easy. You know, making a mess is easy. Destroying a building is easy. You can destroy a building very easy. You know, you see those on the videos. You know, they put some charges there, and they can bring down the building. Let's say for demolition. Demolition's easy. However, building it is not so easy, right? Building it, we're going the reverse. And so, you know, making a mess is easy. I'm good at that, but getting it organized is a lot of work, because you have to overcome the entropy. Overcoming, it's like lifting. You know, you have to lift this weight up. It's work. And so, why? It's because of entropy. Entropy is favorable. However, there's a limit to that. You know, and that limit is when it becomes too unfavorable in terms of energy. We have to balance out these factors. And so if delta H of solution is much greater than 0, then solution formation is unfavorable. In other words, if we have to climb too high, we can climb up a little bit, no problem. But if we have to climb up too high, then it's not worth it anymore. Entropy can't overcome that. And so it's a balance between entropy and energy. That's one way of thinking about it. So do you guys recall the first law of thermodynamics? First law of thermodynamics has to do with energy. Yeah, conservation of energy. Energy can be neither created nor destroyed. That was the first law. The energy content of the universe is fixed. However, for the universe to go on, do you know what has to happen to the entropy? It has to increase. So the entropy of the universe continues to increase. If the entropy of the universe stops increasing, then everything stops. There's no more driving force for anything. And so what it boils down to is this. We know something is favorable when the entropy of the universe increases. And the entropy of the universe is going to increase by minimizing energy and maximizing entropy. Now, energy is also ordered or disordered as well. And so there are different entropies of energy. So for example, we could have a pen up here. This would be called gravitational potential energy. Let's say we have 100 joules of gravitational potential energy. Or we could have heat. Heat would just be these vibrations. And we could have 100 joules worth of heat. So what would be more valuable, more ordered, less disordered? 100 joules of gravitational potential energy or 100 joules of heat? Gravitational would be more ordered. The more ordered it is, the more useful it is, the more things we could do with this. So this gravitational, we can have a pulley and pull something up, or we can do other things with it. And so that's the same thing. When we minimize energy here, essentially we're converting things into heat. You know, so when we're going from high chemical potential energy to low chemical potential energy, that energy is released as heat and or work. And so, well, if we have heat, then that's converting, because energy, remember, energy can neither be created nor destroyed. So if we're going down in chemical potential energy, where's that energy going to? That energy is going into heat, usually. And that heat ultimately goes to heat. And that heat is higher entropy energy. And so minimizing energy, that is this potential energy, is actually maximizing energy disorder. But anyway, that's Chem 1B, so I'm not going to talk about it much anymore. So for example, let's look at some numbers here. If we look at sodium chloride is very soluble. And let's look at the numbers for sodium chloride. So for sodium chloride, we have to break solute-solute. Well, solute-solute is going to cost you a lot of energy, the lattice energy, right? You have to break all the ionic bonds. And then we got to break solvent-solvent. So we got to make room for the solute. So we got to break apart the water molecules. So that's hydrogen bonds and dispersion. And then we form solute-solvent. Solute-solvent, these are going to be solvated or hydrated ions. These are very stable. That's very favorable. But are they as strong as ionic bonds? No. Because overall, what's going to happen, this is another Hess's law. This isn't exactly the same. This is just using the data we know. Overall, delta H of solution is plus 5 kilojoules. Plus 5 kilojoules is going up in energy. That's unfavorable. So what's making this favorable? What's entropy? Now we got to weigh this. When we weigh energy and entropy, then we use this. And so how do we weigh this? This is in Chem 1B. The way we weigh this is by using delta G. Delta G will factor in both these terms here and allow us to predict whether it's going to be favorable or not. So for something like sodium chloride, it's favorable. But what if we had a stronger lattice? Rather than sodium chloride, let's say we had magnesium oxide. If we have magnesium oxide, the lattice is like 2.5 times that. It would be like 2,500. But the hydrated ions would be better. But the delta H of solution is going to be too big, too endothermic. If it's too endothermic, then it doesn't dissolve. So magnesium oxide does not dissolve. Its lattice is too strong. Entropy is not enough. But for sodium chloride, it's okay. All right, let's take a break now, and then I'll finish this up, and then we'll do the. All right, even though sodium chloride energetically is not favorable, this is plus 5 kilojoules per mole, it's still quite soluble. But it isn't infinitely soluble. That is, there's a limit to how much sodium chloride you can dissolve in water. So that would be a non-ideal solution. In an ideal solution, there's no limit. And so an ideal solution would be like water and water. Is there any limit to how much water you can mix with water? No. You can have an infinite amount of water mixed with water. Well, there are solutes that are very water-like, like methanol. Methanol is very water-like, and so it turns out there's no limit to how much methanol you can dissolve in water. It's unlimited. Same thing with ethanol. Ethanol is miscible. We call that miscible when it's infinitely soluble. Ethanol is miscible in water, meaning you can dissolve an infinite amount of ethanol in water. Pretty soon, what becomes the solvent, what becomes the solute flips. So initially, it's water is the solvent, ethanol is the solute, but as you get more and more ethanol, then you're going to have mostly ethanol and a little bit of water, and so it flips. Propanol is less soluble, butanol is less. When you get to pentanol, we call pentanol immiscible. Trying to mix pentanol with water is like trying to mix oil and water. You know, pentanol's got a 5-carbon chain, and so it's very hydrocarbon-like, very oil-like, and so it doesn't mix. Instead, pentanol would mix much better with something like benzene. You know, benzene's nonpolar. Pentanol's fairly nonpolar except for the alcohol, which is very polar. And so we can look at this. For example, here's benzene, here's toluene. When you look at benzene and toluene, they're very similar. And so what you would suspect is benzene and toluene would be miscible in one another. And so two components of a nearly ideal solution, these are near identical, you know, and they're miscible. Something like chloroform and acetone wouldn't, you know, be miscible. These are less ideal. This would be a non-ideal solution. So there's going to be a max, a limit. But we would end up with a, they call this hydrogen bonding. Would you call that hydrogen bonding? What is hydrogen bonding? Hydrogen bonding is when hydrogen is bonded to what elements? The three most electronegative elements, which would be oxygen, fluorine, and nitrogen. When hydrogen is bonded to one of those three elements, it's so polar it de-shields the hydrogen, and it de-shields the proton on hydrogen. So what we have is a partially exposed proton, which makes it very polar. But when you look at this hydrogen is not bonded to oxygen. This hydrogen is bonded to carbon. Is carbon electronegative enough to de-shield the proton? No. And so this is not hydrogen bonding. This is a dipole. This is a dipole-dipole attraction. We have a dipole on chloroform and a dipole on acetone. But it's not hydrogen bonding. I don't know why they're calling it hydrogen bonding here. This wouldn't be so ideal. Here we have acetone and carbon disulfide. And acetone and carbon disulfide is neutral, it's nonpolar. Acetone is polar. And so this would be dipole-induced dipole attraction. Normally dissolving things isn't so easy, you know. So for your unknown, it was fortunate it dissolved in water, but what happens if it doesn't dissolve in water? What do you do next? Hot water. If it doesn't dissolve in hot water, then what? Normally I would go maybe hot water, and then I'd go ethanol, and then hexane, or carbon disulfide. So, for example, if your unknown were wax, I had to dissolve some wax before I used carbon disulfide, which is liquid. And the wax dissolved fairly easily in carbon disulfide. And so what we're doing is first we're looking at polarity. You know, first try water, the most polar, and then ethanol, which is a little less polar, and then hexane, which is not polar at all, or carbon disulfide. Hexane smells a little bit better than carbon disulfide, but both of them don't smell very good. And then if those don't work, those would be physical. Then we might try acid, which would be more of a chemical dissolution process where the acid attacks something, or base, you know, etc. So we try different things. And so this is, again, physical process, physical dissolution. Now, the reason you see all these, like delta G is called Gibbs free energy, S is the entropy, Cp is the heat capacity, is in chapter 13. Chapter 13 is thermodynamics part 2. Normally we do thermodynamics part 2 in Chem 1B, and so I skipped it. So all this stuff you can skip too. We're not going to worry about this. These are all thermodynamic calculations discussed in Chem 1B. More thermodynamic calculations discussed in Chem 1B. Skip that. Here's some ion dipole modeling. So we have some ions surrounded by waters. Okay, now we're back. So we're going to look at the dissolution process. We have some more vocabulary. This is called, this is just the pure liquid. When we have water here, we're going to have this red arrow is dissolution. We're going to get net dissolution. As the concentration of solute builds up, then some of the solute particles can strike the surface and redeposit or precipitate. And so the opposite of dissolution is precipitation or crystallization. Here. As the concentration builds up to a certain level such that the rate of crystallization, that is, the solute particles stick and become stuck, is equal to the rate of dissolution, that is, the particles break off, we've reached a state of dynamic equilibrium. When we reach a state of dynamic equilibrium, dissolution and crystallization never stop. But the concentration doesn't change. So the concentration here and the grams of solid particles here don't change. But if you look at the crystals are always changing because you're dissolving some and replacing those with new crystals. So that's the dynamic equilibrium of dissolution. All right, when we try to dissolve solids, we first try room temperature water. If that doesn't work, we try hot water. And here's a graph of solubility versus temperature. And you can see the solubility increases as the temperature increases. So we might have success there. Some things show a dramatic increase. Other things, a less dramatic increase. And some things actually decrease. This is endothermic, this is endothermic, 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 endothermic. However, this dissolution process is actually exothermic. And so if it's exothermic, we want to remove heat, and therefore cooler temperatures are better. And so for lithium sulfate, it's more soluble in cold water than in hot water. But most everything else, it's more soluble in hot water than cold. KNO3 has a dramatic increase there. Fractional crystallization is covered in Chem 1B, so I'm going to skip that. So there's one more thing I want to talk about on this curve. And that is something called supersaturation. Now solubility has two different definitions. And the first one is qualitative. For qualitative, we have three. We have S, I, and SS. S stands for soluble. Soluble means greater than 0.1 molar solute. 0.1 moles of solute can dissolve in a liter of solution. Insoluble, which is I, means that we have less than 0.1 molar when it's saturated. When it's saturated, we aren't going to get any more solution. Solute to dissolve. SS means slightly soluble. And this is about 0.1 molar. So when we do this qualitatively, we wait until we saturate it. So this is just pure liquid solvent. This is an unsaturated solution. It's unsaturated because more solute can dissolve. But once we hit the limit, then this is called a saturated solution. Once it's saturated, then we determine how much dissolved. If it's greater than 0.1 moles per liter, then we call it soluble. If it's less than 0.1 moles per liter, we call it insoluble once it's hit saturation. Or if it's around 0.1, then we'll call it slightly soluble. There's one more, and that's called supersaturated. supersaturated happens like this. Let's say we dissolve some KNO3. And so at room temperature, how much KNO3 dissolves? This much. And then we heat it up. Let's heat it up to 50, and we dissolve that much, so a huge amount. And then we cool it down. As we cool it down, the solubility decreases, and any excess solute should crystallize or precipitate out of solution. But sometimes nucleation is difficult. Nucleation, all the ions have to be aligned just right. One solid that's hard to get nucleated is sodium acetate. That's because of the acetate ion. When we look at the acetate ion, you know, it's got a shape to it. And that shape, it has to be perfectly lined up with the sodium. Sodium ions are no problem. You know, those are just spherical. And so there's no shape to it. But the acetates have to line up perfectly with the sodium. It's like water. You know? And sometimes it's very sluggish. And so let's take a look at a supersaturated solution here. So what they did was they heated this up and saturated it. You could dissolve a lot of sodium acetate in warm water. But then they let it cool down. When they let it cool down, then all that extra sodium acetate should precipitate out. But the problem is nucleation sluggish because the acetate ions have to line up perfectly, and it's hard. And so we don't see any nucleation and growth here, even though it should be happening. This is supersaturated. There's way too much solute in here. And so to help nucleation, what this person's going to do is they're going to drop a seed crystal in there. So let me fast forward and see. And so they dropped a seed crystal in here, and the seed crystal just provides a template for the ions to stick to. And so we don't have to nucleate a brand new crystal. That crystal's there and it's going to start it. So once you drop a seed crystal in there, then growth should happen rapidly because now it has a template and then it can just add on there. So this is real time here, and this is the crystallization or precipitation that's happening. And it happened very rapidly. And so this is all the excess solute. So if I warm this up, you can redissolve all that excess solute. But when you cool it back down to room temperature, that's way too much. And it'd be way oversaturated. So that's supersaturated. This also happens with gases too. Nucleating CO2 bubbles is sluggish. And so we have something called Henry's Law. Henry's Law is just pretty intuitive. Let's say I have sparkling water here. And do you know what gas is in here for sparkling water? Yeah, this is pure CO2 gas. And the pressure is going to be about 1 atmosphere. So we have about 1 atmosphere of CO2. What Henry's law says is that having the gas pressure here is going to force CO2 molecules into the liquid. And so Henry's law basically says this: the more pressure, the more CO2 is going to be driven into solution. And so Henry's law just says this: that the concentration of the gas is equal to the Henry's law constant times the partial pressure of that gas. So if we double the partial pressure, we should double the concentration.
Is this referring to concentration in the solution?
Yeah, concentration in the solution. The Henry's law constant is going to convert it to molarity, usually. We're not going to do any Henry's law constant calculations. Given by K. Here, let me scroll this up so we can see Henry's law. This is Henry's law. The concentration of the gas inside the liquid is equal to the Henry's law constant, K, times the partial pressure of the gas. K depends on what the gas is and what the solvent is. So we get the K value for CO2 in water. What happens though is, what happens if we open the container? Yeah. Now we'll have 1 atmosphere of air. 1 atmosphere of air has barely any CO2 in there. So the partial pressure of CO2 just dropped dramatically. But you still have all this CO2 dissolved in the water. But Henry's law now, you know, earlier we had so much CO2 being forced, so we have dissolution and outgassing like this. Here, now the dissolution rate is very small. And so what's going to happen, this is supersaturated. And so all that excess gas in here has to degas out of here. But it's a little bit sluggish because nucleation is difficult. How can you help nucleation? One way you can help nucleation is by shaking this. If you shake this up, then you can get a lot more bubbles to nucleate. And then it'll degas much more rapidly. Other ways you can nucleate this is by adding some salts in here. Or menthos, you know, the menthos candy, you put menthos in here. Menthos has an intricate structure and has lots of surfaces for nucleation of bubbles. Or you could put a boiling chip in here. Boiling chips have lots of corners and edges where bubbles can form or nucleate. And so eventually this will degas, slowly or rapidly, depending on how fast nucleation occurs. The effective temperature is the opposite. You know, as we increase temperature, the solubility will decrease as solubility increases. So if I heat this up, will that increase the amount of CO2 or decrease the amount of CO2? If I heat this up, will it go flat faster or slower? Faster. Yeah. And so what happens is, as the temperature increases, solubility goes down. And that's pretty much the case for all gases. The solubility decreases. And so this is not water boiling. If you look at the temperature, it's only 79.4 degrees C. Water doesn't boil there under normal conditions. This is air. And air, the solubility of air is going down, so these are air pockets or air bubbles, nucleating and growing there. There's nitrogen and oxygen that's gotten dissolved. Here's Henry's law in action. If I double the pressure, I'm going to double the concentration. If I quadruple the pressure, I'm going to quadruple the concentration. And so Henry's law is just linear, like that. That is, the concentration is directly proportional to the pressure. Okay, here's an application of Henry's law to the bends, divers. Read about that. Okay, 14.6 is the start of colligative properties. So let's take a look at the colligative properties are a collection of properties that all kind of depend on the same thing. They are all going to depend on this first thing, and that is vapor pressure lowering. Let's compare water with a solution. Let's say salt water. If we look at water, and some of the water molecules will vaporize it, and when we saturate it, it's called the vapor pressure, 100% relative humidity. What if I have salt water? Am I going to have as much water vaporize as before? More water or less water vaporize? What do you think? If you have salt water, are you going to have more vaporization, less vaporization, or the same amount of vaporization? Less. It turns out it's less. And so this is called vapor pressure lowering. When we have a solution, the vapor pressure is going to be lowered. And the vapor pressure is going to be lowered by something called Raoult's law. This is it. So this is kind of weird. So let's say the vapor pressure of water in a solution is equal to the mole fraction of water times the vapor pressure of pure water. Let's say it's pure water. Then the mole fraction would be what? 1 is, if it's pure water, it's 100% water. But the more concentrated the solution, the more concentrated the solute, the lower the mole fraction of solvent. That makes sense. The more solute you have, the less solvent you're going to have. And the less solvent you have, the lower the mole fraction. The lower the mole fraction, that's going to lower the vapor pressure. And so this is Raoult's law. When we lower the vapor pressure, that's going to impact. The easiest thing to see the impact in is the phase diagram. The phase diagram is going to map out the pressure and the temperature and the perverted phases. And so in a normal phase diagram, it looks like this. But water is abnormal, and it's abnormal between the solid and liquid line. In a normal substance, the higher the pressure, the more it favors the solid phase. But water is a bit different, because the higher the pressure, which phase of water is favored, the liquid or the solid phase of water? Turns out that the liquid phase is actually more dense than the solid phase. It's because of how the water molecules have to line up. And so this is a bit abnormal. This is for water. And so when we look at water, the higher the pressure is going to favor the liquid phase here, not the solid phase. And that's because of the very open structure of ice. It has a very open structure to maximize the hydrogen bonding interactions. So let's say we have vapor pressure lowering of water. What that's going to do is it's going to impact the position of this. And so if the vapor pressure is lowered, this is the vapor pressure curve here. Which is this exponential thing. And so if we lowered it, here, this is lowered vapor pressure due to Raoult's law. I'm going to see something like this. This would be solid, this would be liquid here. Now let's go to 1 atmosphere. 1 atmosphere is normal pressure. And if we're at normal pressure, then we have the normal melting point. The melting point is when we convert it from solid to liquid. So this is the normal melting point. And the normal boiling point is when we go from liquid to gas. So that would be normal. However, if we have a solution, then what happens is the melting point gets shifted. And the shift is going to result in a melting point depression. And the melting point depression is going to be given by delta T sub MP, or delta T sub M. And this is just going to equal a constant times the molality of the solute. And so we got the melting point goes lower, but the boiling point ends up going higher. And so we have boiling point elevation here. And delta T BP is equal to a constant, which is going to be a different constant times the molality. And so these are called colligative properties. 1, vapor pressure lowering is a colligative property. 2, melting point depression is a colligative property. And 3, boiling point elevation is a colligative property. And so let's look at some examples. All right, here's the curve showing the vapor pressure lowering. This is not water. This is a normal species. Take a look at the curve here. Water would be tweaked out back. Typical aircraft deicer is propylene glycol, diluted with a spray. So they're using propylene glycol. What propylene glycol does is it gets dissolved in the water. When it dissolves in the water, it lowers the melting point. If it lowers the melting point, then it's going to melt easier. And so we call propylene glycol antifreeze. So propylene glycol is the eco-antifreeze because propylene glycol is not terribly poisonous. The problem is you don't, antifreeze, people put it in their car engines and then end up dumping it in the street. They dump it in the street, then it contaminates groundwater or contaminates the ocean. But propylene glycol is an additive, food additive. Propylene glycol is a synthetic food additive. And propylene glycol is an alcohol, and so it's very soluble in water. We want something that's very soluble. In fact, we want something that's miscible in water so we can get very high concentrations so that we can 1,2-propane diol is another name, etc. is a dialcohol. Propylene glycol is sometimes confused with ethylene glycol. Ethylene glycol is the old antifreeze. And ethylene glycol actually has 2 carbons. Propylene glycol has 3 carbons. Both of them have 2 alcohols. And so this is ethylene glycol here. The problem with ethylene glycol is it's toxic in high concentrations. It has a sweet taste, but you don't want to eat this stuff. And so they're trying to replace ethylene glycol, which is very soluble in water, with propylene glycol. And so it would be more eco-friendly, antifreeze. But that's, you know, for cold winters, we want antifreeze so the coolant in your engine doesn't freeze. You know, we need it for the melting point. But in the summer, we don't want antifreeze. In the summer, we want coolant. And so for coolants, we want the boiling point to be as high as possible. So do we need to drain, you know, do you need to drain out all the coolant? Actually, all the water out of the radiator and replace it with a coolant versus an antifreeze? And it turns out no. You know. It turns out propylene glycol and ethylene glycol work at both. If we lower the melting point, that's going to help prevent freezing. So this is your anti-freeze. Lower the melting point, we aren't going to get freezing until much lower temperatures. But at the same time, it raises the boiling point. If you raise the boiling point, then that's a coolant, because liquid water has much better thermal conductivity than gaseous water. You know, so we need to keep it liquid, because if it turns to steam, it's not going to cool things very well. And so boiling point elevation. So one big application, this is called melting point depression or freezing point depression. And boiling point elevation is as an antifreeze slash coolant in your automobile. This is also the reason why they salt the roads and that kind of stuff. All right. The next colligative property is osmotic pressure. Osmotic pressure is pi, the symbol, and that's just the molarity times R times T. When we look at the molality and the molarity, that's the molality and molarity of all solute species. So we have to look at the electrolyte properties to see how it splits apart. And so let's take a look at these. So the molality and molarity depend on all solute particles. So when I look at sodium chloride, if I had 1 molar sodium chloride, the concentration of solute particles isn't 1 molar. If I have 1 molal sodium chloride, we'll go with molal, then I expect 2 molal particles, because each sodium chloride is going to split up into 2. That is 1 sodium and 1 chloride, 2 particles. If I had lead-2 nitrate, I expect that to split up into 3 ions. 1 lead-2 and 2 nitrates. And so you should go to 3. All right, one of the complications that happens is this. We have ion-ion attractions. When we have ion-ion attractions, then they aren't independent. And so the higher the concentration, the more ion pairing we have. So for sodium chloride at 1 molal, about 10% of the ions are paired. That is, they don't behave independently. They behave as paired. Now, this gets worse with higher concentrations. Magnesium sulfate has higher concentrations. Ion pairing is much more significant. So for magnesium sulfate at 1 molal, about 50% of the ions are paired. That is, they don't go individually, they go as a pair. And the same thing with lead-2 nitrate. We get ion pairing attractions that are more severe there. And so this is what the ideal is, but this is what the actual concentration is. Now, actual concentration, the effective concentration, is called the activity. And so the effective concentration here is called the activity. And the activity oftentimes is different than the stoichiometric concentration. So for sodium chloride, we expect a stoichiometric concentration of 2, but because of ion pairing, it isn't. It's a little less than 2, and it has to depend on the activity, which is the effective concentration. And so for these types of calculations, we need to do more work. We can't just use the stoichiometric concentration. And so this is a problem at higher concentrations. So for example, if we were looking at pH calculations, we're good. From pH 0 to pH 14, that's about 0.1 molar acid to 0.1 molar base. We're good. But when we go to higher concentrations, higher than 0.1 molar, then we got to watch out for ion pairing interactions. Those ion pairing interactions are going to decrease the effectiveness of those. And so when we're outside the range of 0 to 14, then we have to do more involved calculations. And so this is why when a lot of people think pH, they only think 0 to 14. Well, no, that's not the case. We can have pHs less than 0 and pHs above 14. And so in other words, we could have negative pHs and pHs greater than 14. But when we do those, we have to do these effective concentrations and activities which are beyond the scope of Chem 1A. They're also beyond the scope of Chem 1B. So we just look at a chart like this and see we're going to be in error a little bit in our calculations. But those are the concentrations we should be using in these calculations. The concentrations we should be using in these calculations are the effective concentrations. Now let's look at osmosis. Osmosis, we can do some simple interpretations of it. Over here, what we want to do is we want to equalize the concentrations. So what we see here is the concentration is much higher above than it is below. So we're going to get net migration of water molecules because we want the same potential. We want the same concentration. And so the water is going to go from the less concentrated to the more concentrated. So one example we can see that in is this. If we put a blood cell here in an isotonic solution, isotonic would be 0.9% M over V sodium chloride, then the blood cell should stay stable because the concentration out here is the same as the concentration in here. Although the intracellular fluid isn't sodium chloride, it's going to have the same solute concentration when I look at all the solute particles. And when the concentrations are the same, there's no net. You know, the water going into the blood cell is the same as the water coming out. However, if I increase it, this would be that would be isotonic. If this is hypertonic, that is, the solution out here is like brine. It's salty. And if it's like this, what happens is the cell shrinks because the concentration out here is much greater. It's hypertonic than the concentration in here. So we're going to have net migration of water out of the cell, and the cell shrinks. As the cell shrinks, we call it crenation. We get crenation of cells. Here, we put it in, let's say, hypotonic. If we put it in hypotonic, hypotonic is like distilled water. And so the concentration inside the cell is greater, so we're going to get net water coming in. Now, it's going to swell and swell and swell, and eventually it's going to pop. And so we have lysis. Lysis is when the cell membrane breaks and the contents spill out. So here's a normal red blood cell. And so this must be in an isotonic solution. What happened to this one? This must be in a hypertonic. Water, this is pickling. And so you make pickles by putting in salt, really salty water. And so the cell's shrinking here. This one's growing. What's happening here? This must be in a hypotonic solution, in other words. So that's one application. The other application is reverse osmosis. So normally the water wants to flow left to right. It's going from pure water, and we need to dilute this salt water. But what you can do is you can put a pressure greater than the osmotic pressure, and that's going to force the water backwards. And so as long as we put enough pressure on here, we can purify the salt water by forcing the solvent to go the reverse of what it normally does. So that's reverse osmosis there.
So how would you like define osmosis? Is it just like the transfer of water or liquid through the membrane?
Yeah. That's one way to define osmosis, through a membrane. We're going to have a membrane. The other way of defining it is by pressure, vapor pressure lowering. Here, and an imbalance of pressures. So if we put a membrane here, over here we have just pure water. Over here we have salt water. And so the other way of defining osmosis is the salt water is going to have a lower vapor pressure. The pure water is going to have a higher vapor pressure. The salt water has a lower vapor pressure. Okay. So if the pure water has a higher vapor pressure, what's going to happen is it's going to force water into the other side with lower vapor pressure, get the two vapor pressures to equalize. And so this is why it's colligative property with vapor pressure lowering, because that's one way of looking at it. The other way of looking at it is if it forces water here to equalize the pressure, then it's forcing water this way. And so what we can say is the concentrations try to equalize, but it's the vapor pressure, and not just the vapor pressure, it's the osmotic pressures that are trying to equalize. Does that make sense? So there are different ways, there are a number of different ways you can look at it. And so one way is just water transport through the membrane from the less concentrated to the more concentrated.
Is it only consumed with water? Or
No.
everything?
Yeah, everything. Yeah. All right, well, I'm going to stop talking now, and then what we're going to do is we're going to do